you know that if f is an irrotational vector field, then curl of f is equal to 0. It means for a vector f to be irrotational, the necessary and sufficient condition is it must be curlless. If vector f is curlless, it means its curl is 0, then it is called an irrotational vector. But you also know that if f is a conservative vector field, then also curl f is equal to 0. So when f is irrotational, curl f is 0. When f is conservative, then again curl f is 0. So a question arises that if the irrotational and the conservative vector fields are same, because these two conditions are same, when curl f is 0, you say that vector is irrotational, and if f is a conservative vector field, then again you see that curl f is equal to 0. So mathematical conditions are same. So definitely there is a obvious question in your mind that are the irrotational and the conservative vector fields same? So you must remember the answer is no. Actually, irrotational vector field and conservative vector fields are not same. But there is a close relationship, but not exactly same. In fact, when you talk about the irrotational vector field, then this condition curl of f equal to 0 is the necessary and sufficient condition for vector f to be irrotational. It means if f is an irrotational vector field, definitely curl f will be equal to 0. Okay, it is its necessary and sufficient condition. But the same condition, that curl of f equal to 0, is not the necessary and sufficient condition for f to be conservative. It is not its necessary and sufficient condition. Okay, it is necessary but not sufficient. In fact, what is the necessary and sufficient condition for a vector field f to be conservative? Actually, for this, the necessary and sufficient condition is that this field must be a gradient of a scalar function known as the potential function. In mathematical way, you can say that a vector field f is a conservative vector field only if there exists a scalar function phi, which is commonly called potential function, such that this vector field f is equal to del phi or gradient of phi. It means a vector field f, if it can be expressed as a gradient of a scalar function or a scalar potential, only then you can say that vector field f is a conservative vector field. If the vector field f, whose curl is 0, but it cannot be expressed as a gradient of this scalar function phi, then that cannot be a conservative vector field. Okay, so the necessary and sufficient condition for f to be a conservative vector field is what? It must be expressed as a gradient of a scalar function phi. Because you know that if f is equal to gradient of phi, then if you will take the curl of this gradient of phi, you know from the vector identity that curl of gradient of any scalar function is 0. So curl of grad phi will be 0, and then you will get curl f equal to 0. So curl f equal to 0, but when this f is expressed as gradient of phi, then you can say that the field is conservative. But if curl f is equal to 0, but f is not equal to gradient of phi, in that condition the vector field will be only irrotational, not conservative. Okay, so we conclude that actually all the irrotational vector field are not conservative. Are not conservative. It means vector field may be irrotational, but that vector field may or may not be conservative. May be conservative or may not be conservative too. You can consider this example, which I have actually discussed in the previous lecture, that if we consider the position vector r, which is defined by xi plus yj plus zk, okay, then you have learnt in the earlier lecture that curl of r is equal to 0. You can check it from the definition of curl. So as curl of r is equal to 0, so you can say that this vector field r is an irrotational vector field. But at the same time, it is not possible to express this vector r as a gradient of del phi. It means r is not equal to gradient of any scalar function. And so that this r is not conservative. So r, which is position vector, is an irrotational vector, but it is not a conservative vector field. Okay? So it is clear that all irrotational vector cannot be conservative. Okay? But the converse is not true. If a vector field is conservative, that will be necessarily irrotational. Okay? So I have stated here that all conservative fields are irrotational. The reason is what? You can see that if f is a conservative vector field, you have seen that the necessary and sufficient condition for f to be conservative is what? F must be equal to gradient of phi. F must be equal to del phi. And if f is equal to del phi, we know that curl of del phi is equal to 0. And so curl of f will be 0, and curl of f equal to 0 means f is irrotational. So now it is very clear to you that all irrotational vector cannot be conservative. Some of them are conservative and some of them are not conservative. But all conservative vector field are necessarily irrotational. So I think what is the basic difference between an irrotational vector field and a conservative vector field? Definitely you have been acquainted of it. Okay, thank you very much.